Hello everyone, let's talk about states of matter. So this video lecture covers our chapter 13.1 to 13.5. Our first topic is the kinetic molecular theory, and now this is a theory that is based on the idea that all matter is composed of these tiny particles that are always in motion. And it explains what the properties or behaviors of all types of matter, which is solids, liquid, and gases, are the one that we can see. Now, in this chapter, however, we're only focusing on how this theory applies to an ideal gas. Now, an ideal gas is an imaginary gas whose behavior basically perfectly fits all the assumptions that this theory has put out. And in reality, this gas doesn't exist, right? No gas behaves ideally. However, most gases in reality behave close to an ideal gas in the majority of conditions. So we can still use the ideal gas to explain behaviors and properties of gases. Here are the 5 assumptions of the kinetic molecular theory. I want go ahead and pause this video now in order for you to fill in your notes for these 5 assumptions. One thing I want to point out is that gases are consist of a very large number of tiny spherical particles that are very far apart from each other. So the difference between liquid and solid in gases are the fact that how far these particles are together. So in solid, they're very close together, very tightly knit, and then in the liquid, they are slightly further apart, and in the gas, they are very, very much far apart. And these gas particle, as the second assumption says right there, gas particle are in constant rapid motion in random directions. So they are always moving about in random directions, and because they're always moving randomly about very rapidly, they tend to collide with each other and also collide with the container walls that whatever that the gas is contained in. Now, there are no forces of attraction or repulsion between these gas particles, so that's why they can't just move past each other. They don't come together, so they don't attract, or they don't repel or pull apart either when they come into contact with each other. They just move right past. The average kinetic energy of gas particles is depending on the temperature of the gas. I'm going to go over kinetic energy in a different video, so stay tuned. Now we're going into the concept of gas pressure. Now the gas pressure is a result of the gas molecules colliding with these walls of object or container. So I talked about how because these gas particles move so quickly and moves in all random directions, they tend to collide with the wall. They collide with the walls of the object or container that's they're in. And we have a formula that describes what this pressure is, and it is a force over area. And if you take a look at this picture here, this is just showing the pink balls are these gas particles just moving about randomly about, and they're like bouncing off. They collide, these red arrows is bouncing off and colliding with the container that they're in. Now, there are a few factors that lead to an increase in pressure. You can't see the word pressure right there, but I'm saying it's pressure right now. The first one is an increase in force. And if you take a look at the pressure equation, if you have an increase in force, which means you have an increase in the numerator, you will get an increase in pressure. And then when you have a decrease in area, that is when you have a decrease in the denominator, which also leads to an increase in pressure, which is the final answer. Another one where you can have an increase in pressure is actually to increase the temperature. So as you increase the temperature, these particles start moving around a lot more rapidly. And when they are moving around more rapidly, they tend to collide a lot more with the surrounding walls of the object or the container they're in, and because of that, that increases the pressure. So that's when an increase in temperature also gives you an increase in pressure. Now let's talk about atmospheric pressure. Atmospheric pressure is simply just the pressure exerted by the gas particles in our atmosphere as those particles collide with, just say, me, you, my hair, my bed, my my computer, those collision create a pressure, and this pressure is what we call atmospheric pressure. So atmospheric pressure is typically measured by a mercury barometer. So this is what a mercury barometer looks like. Now let's talk about pressure and altitude. If you ever looked at a box of baking mix or even some sort of like dry food, you'll see that it'll tell you the direction for if you live at a higher altitude is a little bit different. And that is because the atmospheric pressure decreases as the elevation increases. So that's why the directions for someone how to prepare the food depends actually on our atmospheric pressure. And because it changes as you go up higher into the mountains, that's why you have to change the way you cook some stuff. Now, there are a few different units of how you can measure pressure here. And these are the ones that you are responsible for. Standard atmosphere is the average air pressure at sea level. If you remember our stoichiometry, going from volume to volume or volume to mass, you might have remember as STP, which is standard temperature and pressure. That's 1 atm and 0 degrees Celsius. So that's atm right here. That's that unit, standard atmosphere. And you also have millimeter of mercury. This is from the barometer that we were looking at earlier. And also Torricelli. The SI unit for pressure is Pascal. There's also kilopascal and pounds per square inch, which is psi. So here's just a little summary of how all of these units are connected. Let's go ahead and move on to how you can convert from one unit to another. The way you do these conversion from one unit to another is very similar to how we do stoichiometry, where we will set up a few different fractions in order for things to cancel out and then for things to keep. So I'm going to give you an example here let's start with 613 millimeter mercury. I'm looking at my conversion factor here that's in the box. I'm seeing that I want to go from millimercury to a atmosphere ATM. So I will set up my calculation so that I have millimeter mercury at the bottom and ATM at the top, because I want millimercury to cancel and ATM to stay. And my final answer here should also be ATM. And looking at my conversion factor here, I see that 1 ATM is 760 millimeter mercury. And when I put this into the calculator, 613 divided by 760, I get 0.807, keeping in mind a significant figure. Now I want to go from 613 millimeter mercury to, I'll say, kilopascal. And I want I'm doing the same thing where I want millimercury at the bottom and kilopascal on top because I want to keep that. Now I'm filling in my fraction by looking at, so 760 millimeter mercury is equals to this much kilopascal. So I'm going to fill that in by that 760 down the bottom and 101.3 at the top. After I put that into the calculator, I should get 31.7 kilopascal. All right, that is how you do these kind of conversion factors. So now it's a chance for you to practice on your own.